Hello and welcome back. In today's video, I'm going to go through the RC timing circuit that's been given in the Art of Electronics on figure 1.38. Now this circuit is really interesting because I think it will encompass quite a few of the things that we've been through in the exercises so far. So this circuit obviously looks at potential dividers. It looks at the charge time and discharge times of capacitors, and then we also have a comparator in the circuit. So I will show you how this circuit works, then we'll build it up and we'll see what the voltages and different points in the circuit are doing. So hopefully this will be a slightly more detailed design breakdown, and hopefully you get to understand the circuit in more detail. Obviously, if you have any questions or any topics you want to bring up, please let me know in the comment section below. So first of all, let me explain to you what the circuit looks like and how it works, and maybe we'll do some simulations to see if it works on paper first before building it. So this is the circuit that has been given to us on figure 1.38 in the Art of Electronics. So let's start analyzing this circuit and let's figure out how it works. Obviously, we have ignoring this switch for now, we have a potential divider that's formed with R1 and R2, and we have a capacitor that's in parallel with R2. And then we have a secondary potential divider that's connected to the inverting pin of the comparator, which is formed by R3 and R4. So we can calculate the voltages that appear on the non-inverting pin first, as this will be the easiest section to look at. We have a power supply voltage rail of 5 volts. So doing the maths on this, we have a 620,000 resistor R3, and our R4 resistor is equal to 360,000, and our top voltage on this potential divider is equal to 5 volts. So in order to calculate the voltage that appears at this node here, and let's call that node VA, we have to assume, first of all, that we're working with an ideal comparator here. This means that there will be zero current flowing in this direction. So essentially we can ignore all of this and just focus on these two resistors here. Now, using the potential divider equation, which is basically V out is equal to Vs times the bottom resistor divided by the top resistor plus the bottom resistor. Which gives us a voltage of 1.84 on this node here. So now let's look at this part of the circuit here, which basically we have a switch. So that means there'll be two states in this. So state 1, let's call that open switch. So when the switch is open, this node is basically not connected, and that essentially means that the capacitor is grounded through the 6.2 mega ohm resistor over here. Given enough time, this capacitor should be fully discharged through this resistor. And the voltage across C1 and R2 should be equal to 0. So that means the non-inverting node on the comparator is also equal to 0. Now in the second case, when this switch is closed, so when this switch is pressed, the 5 volts will be connected to the resistor R1, which is a 1 kilo ohm resistor. So now what you have is a potential divider with R1 and R2, and we can calculate what the ultimate voltage is going to be on this node, or the maximum voltage. So now you have to kind of look at the theory of the capacitors. From the previous exercises, we've learned that the current through a capacitor is high if you have a fast transient. So which is what's going to be simulated or replicated by pressing this switch. So if you imagine a very high rise rate pulse going through this node, at that time, the reactance of the capacitor is going to be very low. There's going to be a high amount of current flowing through this capacitor. and that will cause this capacitor to start charging. So initially, the voltage drop across this node here when the switch is pressed is going to be 0, but will rise rapidly to a voltage that is formed by the potential divider of R1 and R2. So let's calculate what that final voltage is going to be and then simulate the circuit. The potential divider, ignoring the capacitor, is going to be very similar to before. However, obviously the components are R1 and R2. R1 is equal to 1000 and R2 is equal to 6.2 million. So 6200123. Top of the voltage, assuming this is a very good switch, and so you've got 0 ohms resistance here, you're going to have very close to 5 volts as your final voltage on this node because of this very high resistor here. So what will happen is this capacitor will charge up to approximately 5 volts when you press this switch. So now let's look at the two individual bits, the potential dividers in isolation. So obviously this is the first part of the circuit which controls some of the timing, in that we have the capacitor here and we have the dissipation resistor. So obviously when the switch is open and the circuit's been sitting there for a long time, the voltage across the capacitor will be equal to 0, as it will be discharged through this resistor and a little bit through the comparator or the op amp. But let's ignore that for an ideal case. So the voltage here is 0, and then someone presses the switch. So as soon as the switch is connected, this resistor will be connected to 5 volts, and you will have a large current going through this capacitor, and the capacitor will start charging. From what we worked out, the capacitor will charge up to 4.99 volts and will stay there as long as the switch is connected, as the resistor will continuously charge. Obviously, as the voltage is building up on this capacitor, this resistor will start leaking some of that current, but this resistor is significantly smaller, so the charge will occur, the voltage on the capacitor will build up. And then when the switch is released, this becomes open circuit, so the voltage on this node and this node will be the same, as you will not have any current going this direction. And the way this voltage will dissipate will be defined by this characteristic curve here. And the time taken for the voltage to get to 37 volt, 37% of 4.99 is equal to R times C, which in this case is 10 microfarads and 6.2 mega ohms. However, we can calibrate the timing to be anywhere on this graph, and we can adjust the timing to our requirements using this equation here. Now let's look at the second half of the circuit. I think it's important to maybe start looking at this point over here. So we know this node over here is going to exponentially decay to 0 volts from 4.99 volts. When this node is higher than this node, so this node is the non-inverting input and this node is the inverting input. When the non-inverting input is higher than the inverting input, your output will be high, will be clamped to basically, or will be close to 5 volts depending on the performance of the op amp or the comparator. And as soon as this node falls below the value of this node, so as soon as the non-inverting input falls below the inverting input, your output of the comparator or the op amp will fall to 0. So obviously we can set the voltage of this node using the values of these two resistors here. It is a good idea to have the value of the resistors to a high value, as this reduces the current draw, obviously if this was a battery application or something like that. In the case I'm doing, obviously this doesn't matter too much. So that's basically the full explanation of this circuit. So what I'm going to do now is build up this circuit. However, I don't have all of these resistor values available to me. So as I do the simulation, I will be doing the simulation with the values of resistors that I do have. Obviously that will change the timing parameters, but the circuit will obviously behave the same way even if you are using different components. The only thing that would change is the voltage, the fixed voltage that appears here, and the rate of decay on this voltage. So let's now get to the simulation. So the way I'm going to make the switch is with a resistor that I'm going to change the value depending on the time. For a time, let's say of less than 1 second, I'm going to set the value of the resistor as equal to a very high value. So time less than 1, the value is going to be 10 gig. And then if that's not the case, then I'm going to check if the value is more than, if time is more than 2 seconds, then the value is going to be again 10 gig. And then if that's not the case, then I'm going to set the value to be equal to 1 milliohm. We'll see if that works and test it out. So let's set the timing for this circuit as 10 seconds. So at 1 second, obviously the switch should come on. So you can see it is coming on at 1 second, the switch comes on. And the value of this obviously goes very high. The up pump that I used before wasn't working properly, so I've changed that to this one. So you can see the reference voltage is set to roughly 1.6 volts, and then our switch comes on at 1 second, which causes this voltage to go up to approximately 5 volts, and then the switch is turned off at 2 seconds, which then causes the output voltage to decay over time, and you can see the output should stay on until this value falls below that. Obviously this means our circuit time is too long, so we can't see it in the simulation. So what I'm going to do is increase the simulation time to maybe 30 seconds and see if that helps. So obviously that is a lot better. First, let's zoom into this section here. You can see there is a small amount of time it takes for the capacitor to charge, and that is dependent on this resistor value here. If this resistor value was bigger, this capacitor would take even longer to charge up. And if it was smaller, it would charge up faster. With a value of 1 kilo ohm, we get a reasonable time to turn on. We basically need the non-inverting input to go above the inverting input to switch the output to on, and that obviously happens very quickly, as you can see over here. The output switches on in roughly 3 milliseconds, which you can see from here. So that is the starting point, and that is when the output switch is on. Now finally, let's look at when the output switch is off. So you can see the switch is maintained on for 1 second, which you can see over here. So at 1 second and at 2 seconds, the switch is on. So you've 5 voltage on the non-inverting pin. Obviously the voltage on the inverting pin is always fixed because we've got 2 resistors on it, and that value is fixed to 1.6 volts. So as soon as the switch is released, the output on this capacitor, the charge on this capacitor starts to dissipate through this resistor here, and basically as soon as the voltage across the capacitor and the resistor and on this non-inverting pin drops below the inverting pin voltage, the output switches off. So obviously that means we can control the output voltage using the combination of these two resistors and also the value of these two components here. So we can increase or decrease the resistance value. So if we decrease the resistance value over here, then what that would mean is the full voltage over here would decrease. So the starting voltage would be lower. But it would also mean that when the switch is released, the capacitor would discharge faster. So let's try that now. So if I was to change that to 100 kilo ohms, you can see there is a bigger difference now on the charging voltage. So this now only goes up to 4.95 volts rather than 4.99 volts. And also it discharges, the capacitor discharges through this resistor a lot faster. So the time is now changed from, which was more than 20 seconds, I think, previously. It's only now a bit over 1 second on time for the output. If we change the value of any of these resistors here, we can basically increase the reference point. So I'm resetting this value back to 1 meg and changing both of these to 1 kilo ohm. And you can see we've changed the reference point over here to 2.5 volts. So as soon as the value of the non-inverting falls below 2.5 volts now, the output will switch off. So we've reduced the time from what it was previously to this point here. So previously the value of the on time was 12 seconds previously. If you change that to 100 kilo ohms, then that would change to a smaller value. So the values that you see on this circuit here are the values I have available. I don't have this op amp, but I will be using a different op amp, LM358. I did have a comparator, LM393. However, I think I may have a bad batch, as this didn't work with the circuit that I was showing you here. So let me show you how I build up the circuit and then the timing diagrams and everything. Show you how the circuit works. So this is obviously representing the switch. If I connect that to 5 volts, the LED comes on. And you can see it stays on for a certain amount of time and then it should turn off by itself, as you can see there. And the time that it turns off depends on your voltage that's on this node here, which is obviously determined by your R3 and R4. So I've got 1.617 there. When the switch is connected, the node with the capacitor obviously is equal to 5 volts, But as soon as I remove the switch, you can see that it starts to drop and will eventually fall less than 1.61, and the LED will turn off. So you can control the timing on how long the LED stays on for by changing either this voltage here, or by changing this resistor, or changing this capacitor. You can also change the final voltage that's on here. However, if you increase the value of this resistor too much, it may take too long to charge the capacitor value. So you probably get a delay on when the LED turns on. So if I was to increase the value of this resistor, then we might get a delay at this point when you press the switch, as there'll be a limited amount of current going to the capacitor. So on this, we can see what the timing is. Obviously, pulling in cursors over here, and we'll compare that to the simulation. So we are getting roughly 8.1 seconds. Compare that to our simulation, which had the same components. We were getting a on time of approximately 12 seconds. So obviously, a lot of this is dependent on the tolerances of the components and also the comparator that we've used. Obviously, I don't have the comparator that I used in the real life available on my models for LT Spice. And there'll be tolerances on the resistors and the capacitor. The capacitor will likely have a bigger tolerance than the resistors as well. And that plays a crucial role in the timing. Hopefully the circuit was useful. Let me know your thoughts if you have any questions on the comment section below. Thank you for watching.